I shall say a few words about myself, yeah? Shall I?
Yeah. Of course.
Okay,
Okay.
cool. Good. Well, thanks a lot for inviting me. It's a big honor to be the speaker in your webinar today. So my name is Christoph. I'm very much interested in paleoseismology and tectonic geomorphology, in earthquake geology. And I try to use as many methods as possible to look on the same topics, like how active tectonics do work in certain regions, and how we can learn about strong earthquakes that happened somewhere in the past. So my main areas of interest have, well, in the past it has been a lot the Tian Shan or Central Asia um, in general. So I did a postdoc in Cambridge on that topic, but still today I'm very much interested in that. And whenever I have the chance, I go to the field to Central Asia and look at these wonderful falls over there. And now here at the University of Jena, I have another project that focuses on the active tectonics of the European Alps. And there I look at strike slip faults in Slovenia and at thrust faults in Austria and in Italy. And this area is very slowly deforming, so the historical earthquake record is not very good. And therefore, I use a lot of paleoseismology techniques or tectonic morphology and other techniques to find out about big earthquakes there. But today, I would like to talk about the Tian Shan to you. And really, this talk has a focus on two different things. So the first thing I want to get across is how we can use different data sets and different methods and how we should combine them to get the information that we need to have to understand the earthquake hazard. And the second focus and the second topic I'd like to bring across is how many faults out there in the Tian Shan have to be evaluated and analyzed in order to get the overall tectonic picture right. So I will talk about combining remote sensing and fieldwork to understand what's going on with the earthquake hazard in the Tian Shan. So I'll try to stick to 45 minutes and we'll see. So this is our area of interest. So here you can see that we have about 40 millimeters of north-south shortening between India and Eurasia in total. And here, that's the area I will talk about today. There we have about a quarter of that. So about 10 to 15 millimeters of north-south shortening is taken up here in the northern Tian Shan area. So this is Tian Shan, this big mountain range here, and I'll talk about this bit today. So 10 to 15 millimeters of shortening per year in this area. And so we come straight to the first topic. Here you can see a map of the northern Tian Shan, and here you see Almaty, the former capital of Kazakhstan. Now the capital has been moved, but Almaty still is an economic center of the country, and it's home to about 1.5 to 2 million people. So it's a very big city for Central Asian standards over there. And here you see Bishkek, the capital of Kyrgyzstan. And it turned out actually that the city of Almaty has been destroyed 3 times by big earthquakes in the past. So what you see here, this star, this is the epicenter of an earthquake that happened in the year 1887. And it's called the Verni earthquake because back then Almaty was called Verni. And it had a magnitude of about 7.3. The epicenter was close to the city, so the city was destroyed, quite a big earthquake. The interesting thing with that earthquake is that we never found any surface ruptures of this earthquake. So the epicenter was not on the mountain front, but it was somewhere in the interior of the mountains, and it's not yet clear if there were any surface ruptures. We know about landslides and these things, but not about surface ruptures. And then just 2 years later, in the year 1889, an even bigger earthquake occurred, magnitude 8, and that's the famous Chile earthquake. Now, this earthquake caused huge surface ruptures, more than 100 kilometers. And these blue lines here, these are the surface rupture traces caused by this magnitude 8 earthquake. And you can see it was rather far away from the city, but because the earthquake was so incredibly strong, magnitude 8, the city was very heavy hit and damaged, and well, it was hit again by a strong earthquake. And then in the year 1911, just about 22 years later, another magnitude 8 earthquake occurred in the Tian Shan, and that's the Chongqing earthquake, and this is the surface rupture trace of this earthquake. And you see it's even longer than the one in 1889, up to 11 meters of displacement and more than 100 kilometers of surface ruptures. And again, the earthquake was not right beneath the city, but rather like a few kilometers away, about 50 kilometers away or so. But because the quake was so strong, Almaty got heavily damaged and almost destroyed. So within 25 years, the city had suffered from the severe earthquake damage. But the interesting thing is here that the big mountain front fault that marks the northern edge of the Tian Shan, this fault has not even ruptured. So Almaty was destroyed 3 times, but always by faults that are a little bit away from the city. So we were interested, of course, in the mountain front fault and see if this one also produced strong earthquakes in the past. And what I show you now in the first part of my talk is results from different parts along the mountain front. So all these blue dots here, these are investigation sites, and I'll talk about a couple of them and show you what we have found to understand the earthquake hazard posed by this big fault. But first, a few slides on the general setting. So here you can see a view towards the mountains. So that's the arrow indicating the view direction. So here the stable Kazakh platform is an elevation of about 700 to 800 meters. And then in the background you see the mighty Tian Shan. And even here close to Almaty, the mountains are 4,000 meters, almost 5,000 meters high. So there's about 4 kilometers of topography. So quite spectacular. And another thing that becomes important later in the talk is that we see a lot of like less covered foothills. So foothills covered by aeolian sediments, and they cause a problem because they obscure the fault trace. And they are about, let's say, 400 or 500 meters high in front of the proper mountain front. So that's what the area looks like in the field. So now let's start over here. Here on this site, we identified a couple of fault scars. So here you can see one. It's not very nice, but I show you a profile in a minute. And in order to analyze these fault scars, well, we looked at satellite data first, of course. So we used the SRTM digital elevation model with a resolution of 30 meters. And we also went there in the field and used our drones to make photogrammetry models with the structure from motion technique. So this is the SRTM data. You can see the fault trace, but not all the interesting details. But here on the drone DEMs that we produced, you can see the fault trace right here marked by the white arrows. And this is another DEM. So this is this one here, and you can see where the fault trace is running. And now from these high resolution drone images with a DEM resolution of a few centimeters, we measured the height of the fault scarp in the alluvial fans. And we made a geomorphological map. So we find different generations of fans. T1 is the youngest generation, and then we find older fans, T2, and even older fans, T3, and the oldest ones are T4. And we could map them with the remote sensing techniques. And with the drone images, we measured the height of the fault scarps. So for example, here we have a 7-meter high fault scarp offsetting these alluvial fans. And there's another small scarp here with about 1 meter offset. And then here's another profile. I think it's this one here. And there we find a 6-meter high fault scarp. So by doing this, we can get an idea on how big the earthquakes can get there. And if we would date these surfaces, we could also measure its slip rate. And we did something similar in other places along the fault. So for example, here on the eastern tip of the fault, we also found very nice fault scarps. Here you see a 10-meter high mighty fault scarps. And we also measured the vertical offsets. However, in this case, we couldn't fly our drone because it was too windy and actually because I crashed the drone in the wind. So we had to do something else, and we used a differential GPS that we could walk around in the field to measure profiles along these fault scarps, and we found offsets between 2 and 24 meters. So some fault scarps were small, so perhaps single event earthquakes and fault scarps, and some were really large that probably record fault motion in many different events. And we did this kind of investigation in many places along the mountain front. However, doing this only works where the landscape looks like this, but it's really difficult to do this in Almaty, where everything is built, there's infrastructure and houses and so on. So there we had to do something different. But we already knew from the ALOS DEM that there's a scarp just visible in the city center. So the ALOS DEM also has a resolution of 30 meters, and it's the one freely available from the Japanese Aerospace Agency. So this DEM told us, yeah, there is perhaps a scarp in Almaty. And when we went to Almaty and had to look, and yes, we saw the scarp in the city, but there was an 8-lane highway on the scarp. So there's no way to dig a hole or anything. And it's really very much altered and not really nice to see. Therefore, we had to go for something different. And what we did is we organized, or actually we bought stereo satellite imagery. And in this case, we went for the Spot 6 satellite. So these images have an optical resolution of 1.5 meters. And if you have stereo satellite data looking at the same spot from different angles, you can produce a digital elevation model with a resolution of around 3 meters. And this is cool because the wide roads in Almaty, they're really big. They're like 30 meters wide or so. So with these data, with 3-meter resolution, we could really map out the fault scarp following the roads. And that's what we did. And we found that in Almaty downtown, there's about 5 meters of vertical offset in the alluvial fan that Almaty sits on. So we could do that. Now, we also want to get a slip rate of the fault, right? So we want to know how fast it slips on average. And for doing that, we would need a site where we can nicely measure the vertical offset of the fault, and where we also have a good way of dating the deposits that are offset. And it turned out that the best site for that is over here, where this little river comes from the mountains and flows into the flat Kazakh platform. And this river has incised, is eroded into the terraces and left this beautiful terrace system behind. So here you can see, well, that's the modern riverbed, and then there's a river terrace T1, and then there's an older terrace T2 that you can actually see on both sides of the river. And there's an even higher and older terrace T3. And behind that, there's an even higher and older terrace T4. So this would allow us to measure the offset and in the terraces. And in these sediments, we could also find something for dating. So again, we took our drone and produced a high resolution elevation model. So here you see the outlines of the drone DEM, and here you see the drone data. And then we measured the offset of the terraces. So the biggest and highest terrace, T4, is offset by 50 meters actually, and T2 is still offset by about 10 meters. And T2 is also where we could date the terraces and get an age. So this is what T2 looks like in the river outcrop, and you can see there are some gravels and even more coarse gravels here at the top. But in between, there's a fine-grained layer that was sandy material, let's say. So we had a very close look into these fine-grained layers, and we found 3 pieces of charcoal here. So the upper, middle, and lower refers to 3 different charcoal samples. And we dated them with radiocarbon, and these charcoals were about 12,000 years old. So this tells us that the terrace here is perhaps a bit younger than 12,000 years. And then combining the vertical offset with the age helped us to measure a slip rate of about 1.2 to 2.2 millimeters per year on average. And the variation here in the slip rate results from the fact that we don't know precisely the dip angle of the fault. So if it's a steep fault, or a very shallowly dipping fault makes a big difference. And therefore, there's this uncertainty here in the slip rate of the fault. But actually now we have a fairly good idea, and a fault that slips about 1 to 2 millimeters is no good news for Almaty. So all the faults in Germany are way slower, and I guess in Korea too. But in the Tian Shan, we actually find a number of faults that have about 1 to 2 millimeters per year. So it's still a slow fault, but in 1,000 years, it accumulates like a meter of strain. Okay, but we also wanted to trench the fault because we wanted to know when the last big earthquake happened. So we also investigated the entire mountain front to look for the best possible trench site. And it turned out that this was surprisingly difficult. So one reason for that is these loess covered hills that I talked about in the beginning, because these aeolian sediments, they blanket the fault scarp, they sit on the fault scarp and you don't see anything anymore. And another problem was that the areas where we expected the fault scarp were now covered by infrastructure or by agriculture, by a big canal, by roads, etc. So for example, here you see on the image the big Almaty Canal. That's an interesting infrastructure project from the 1970s and the 1980s. So it basically collects the water coming from the mountain, and the canal is built all along the mountain frontier until it reaches Almaty. And it's a very important one for irrigation and the water supply for the city. But because of the canal, we could hardly see the fault scarp. So we went back to the archives and we looked at declassified spy imagery from the American spy satellites from the 1960s and 80s and 70s. And this is called corona imagery. And it's freely available. You can download hundreds, thousands of mono and stereo images from the American websites hosted by the USGS or the NASA. And we found an image from 1969. So this image is older than the canal. And there we found that the canal was actually built right on the fault scarp. So no wonder we didn't see the scarp anymore, because the canal is there now. So really, this old imagery, which has a fantastic quality actually, helped us to better map the fault trace and also to identify a good trench site. And then we went there to this place and actually opened a paleoseismological trench. So this is what it looks like. Down here would be the canal, and our fault would produce this little step here. Cannot really nicely see it, but my colleague here, Kanadbek, is standing right on the fault trace, and this was the only excavator that we could find around that would dig us our trench. And now this trench was successful, so we found the fault, and it's currently the topic of the PhD thesis of Roberta Wilkinson, who is sitting here sketching the trench wall. And she's doing her PhD at the University of Oxford with Richard Walker. And that's why I don't talk that much about the trench now, because she'll publish a paper on the trenching results very soon. It's just one thing that I'll show you. Here, of course, the red line marks the fault trace, and you can see it's a thrust fault, so this block went up over thrusting this block here. And I just marked one layer with the blue dashed line. So here you can see a whitish horizon, and you can find it again over here. So these kind of things help us to get an idea on the offset and what's happening in the trench. And Jin, as you just said, there are also people interested in dating techniques here in the seminar today. So we have radiocarbon dates, and we also have OSL dates from the trench. And it looks like the last earthquake is just a few thousand years old. So the fault that Almaty sits on is active, and it had big earthquakes, surface rupturing earthquakes in the past few thousand years. So stay tuned for the paper by Roberta Wilkinson, which will be published or submitted soon, I think. Okay, so this was the story of the Almaty range front. But let's step back a little bit and have a look at the bigger picture of the regional tectonics, what's happening there. So here is the Almaty fault that I just talked about in the past 20 minutes. But as you can see here in this basin, it's called the Ili Basin. So this is the Ili River here, and this is the Ili Basin. There are many more faults. And if you want to understand the local tectonics and the seismic hazard, we have to have a look at the other faults as well, right? And that's what we did. So you can see there are some northeast, southwest trending structures, like this one or this one, and these things are left lateral strike slip faults. So, and then we have northwest, southeast trending things. These are right lateral strike slip faults with a reverse component, and then we have east-west faults, which are really big, and these are classical and pure thrust faults. And well, we had a look at them in the field, but before I take you to the field, I show you another few remote sensing techniques. So here I plotted the available GPS data for the region. And there's this wonderful paper by Zubovic et al. From 2010, who published a multi-year GPS velocity field for the entire Tian Shan region. So these are the GPS velocities with respect to stable Eurasia. And you can see, I think, really quickly that the arrows are getting shorter the further north you go. So the north-south velocity is shrinking. So that means there's some north-south shortening going on here. And also there's a change in directions. So all the arrows here point to the north, northeast. And then here, up here, they all point towards the northwest. And we can have a closer look. So I present two profiles here. So this profile with the rectangle here and the triangle here is this one. And here I plotted the north-south velocities. That's the white dots here. And you can see here in the Ili Basin, these velocities drop from about 6 millimeters per year down to about 3 millimeters per year. So this means there's north-south shortening of a few millimeters per year taken up here in the Ili Basin. But also the east-west velocities change. So these are the black dots here. You start with about like 1 or 2 millimeters of eastward motion, but then if you go across the Ili Basin, you turn into 1 millimeter of westward motion. So there's both north-south shortening, but also a broad left lateral shearing going on here in the Ili Basin. And you can see the same over here, but it's not really that important. So the most important thing happens here in this graph. Okay, so this is what GPS tells us. Without going to the field, we already know that there is shortening and left lateral motion. And then we had to look at big earthquakes, because strong earthquakes, say stronger than magnitude 5.5 to magnitude 6, they allow us to look at them with teleseismic methods. So we can use records, like worldwide records from the earthquake waves, to figure out the earthquake mechanisms and precisely calculate the beach balls here, the fault plane solutions, and the depth of these earthquakes. And we have two observations here. The first is that all the big earthquakes that we analyzed also have northwest slip vectors. So this fits very well with what we see in the GPS, and that's why we also plot the GPS here. And the second important thing is that here in the Kazakh platform, the earthquakes tend to be deep, around 40 kilometers or more than 25 kilometers. But in the mountains, the earthquakes all tend to be shallow, like 17, 18 kilometers, 16, so no more than 20, 25 or so. There's a fundamental difference. In the platform, where this crust is strong and cold, we have a high seismogenic thickness, but in the mountains that are deforming, we have a rather low seismogenic thickness. Okay, but what we also learn is that these observations from seismology don't tell us that much about the Ili Basin. Why? Because there are no big earthquakes there in historical times. So we really have to go to the field. But first, of course, we used remote sensing again. So we used satellite images, we used the SRTM elevation model, we used the ALOS elevation model. And then there's a cool other freely available digital elevation model. It's called 8-meter HMA. HMA stands for High Mountain Asia. And for the highest parts of Asia, there's a free 8-meter DM, which is really cool. So the purpose of that is, I think, glacial research. But if you have a fault scarp in a high altitude, you're lucky and you get these wonderful data also for your faults. And then we complemented these DEMs with drone DEMs and with helikite DEMs to have a closer look. And then we also did, of course, GPS profiling, field mapping, etc. So this, for example, here is a DEM that we produced with a helikite, big fault scarp. It's actually this one here, 8 meters long, 8 meters high, and I think about 60 kilometers long. So it's really wonderful how it offsets here the alluvial fan. And here's a person for scale, so it's a really big thingy. And here's just another fault scarp in the Jungarian Alatau. Again, we have these beautiful elevation models. And we can see one fault scarp here and another one up there. And here you see them in the field, both of them about 15 meters high. And here we can see a profile along these fault scarps and measure precisely the offset. So, and we did this basically on all the colored faults that you see here in the basin because we wanted to find out which of them are active. And it turned out all of them are active actually. So all the ones that we looked at, they all had late quaternary Holocene motion, and parts of them had really big offsets. So all of them are active. So what does that mean? So what's going on there, tectonically speaking? So I made a little sketch to illustrate what we're looking at. So here, this is again the study area in the Ili Basin, and that's our conceptual sketch. I zoom into that now here. So overall, we have north-south shortening, that's indicated by these two arrows here, and a bit of left lateral shear, and that's indicated by these two arrows here. And there are three types of faults taking up the deformation. So first we have east-west thrust faults, and then we have the big left lateral strike slip faults like these ones. And in between, we have these smaller right lateral faults. So how can they be right lateral? Well, we think that these right lateral faulting here works if you have counterclockwise rotations of the blocks that are trapped in between the thrust faults and the strike slip faults. So this is our regional concept for how this basin in front of the northern Tian Shan is deforming. So this is now a brief conclusion for the first part of my talk. So it turns out that the seismic hazard to Almaty comes from many different faults. So this is known from the history of Almaty with its 3 big earthquakes, but also what we see in the field and from our remote sensing studies. We think that Holocene earthquakes on the mountain front fault that Almaty sits on are stronger than 6.8 because that's what we get from the height of our fault scarps and from the offset that we found in the trench. It's likely that these Holocene quakes have been much stronger. Why? Because, as you have seen, the 7.3 earthquake from the year 1887 did not produce a surface rupture. So we think you might need stronger earthquakes to produce that. Also, the fault is really long and it's definitely capable of rupturing in a bigger earthquake than magnitude 6.8, but at least 6.8, we think. And there is an additional hazard from secondary effects. So if there's the earthquake, of course, you have the offset on the fault, which is a catastrophic thing to think about because Almaty sits on this fault. But the secondary effects like landslides and liquefaction, they could be really significant because as you see here in the outskirts of the growing city of Almaty, many houses are built on these loess-covered foothills. So here you see these hills are made of loess. And that's really bad because if there's shaking, these hills are prone to landsliding really like crazy. So this could be really severe. Also, the canal, for example, and all the roads and infrastructure run across and along these loess hills. So if there's a big earthquake on that mountain front fault, that's gotta be a huge problem from many different perspectives. And I hope I could also show you that really combining different methods, combining different data sets and field observations and GPS and seismology really is the key for understanding the bigger picture of what's happening here. Okay, and now if you think, wow, that's rather complicated, I have bad news because there are even more problems. And then now the second part of the talk, which will be much shorter, I'll spend on Kyrgyzstan and illustrate another problem that we found um, in the Tian Shan when studying active tectonics. So now I'll take you to the Susamir Valley. So here again is the mountain front with Almaty that I just talked about in the last 30 minutes. Um, Almaty was used to be called Alma-Ata in Soviet times. Here again is Bishkek. And now we go here in this little intramontane basin, and that's the Susamir Basin. Why is that interesting? Because in the year 1992, there was a magnitude 7.2 thrust faulting earthquake here in the Susamir Basin. And there's a fantastic paper by Suhail Ghosi et al. From 1997 describing the effects of this earthquake to the landslide. And what they actually found is two locations where the earthquake caused surface ruptures. And that's the fascinating thing. One location is here and one location is there. So let's have a closer look at these earthquake ruptures and see why they are really strange. So here I provide just a little elevation map. You can see even the mountains are really high. They're more than 3,000, almost 3,500 meters. And the basin itself sits at about 2.2, 2.3 kilometers. So high up in the beautiful Tian Shan Mountains. And now these, these two red lines here and these, that's all the surface ruptures that happened in 1992. So over here in the west, we found surface ruptures that look like this. They are rather small, about like up to a meter vertical offset of the alluvial fans or so. And their length was a few kilometers only. And they were not even continuous. So there are a few kilometers of surface ruptures here, then there's a little bit of a gap, and there's another set of surface ruptures here. And in total, there were about, but they're reported to be 3 to 4 kilometers. Eleanor Ainscoe found that they were actually a bit longer, and that's published in her 2019 paper, but still they're about like 6 kilometers in total or so. And then there's a huge gap. There's a 20, 25 kilometer gap with no surface ruptures at all. But then there are these surface ruptures, and they look like that. Look at that. Here's two geologists for scale. So these surface ruptures, they were about 3 meters high. And now it's the fascinating thing, they were only 600 meters long. And that's it. Like out of nothing. It's really incredible. So we have the one set of surface ruptures, small ones, a few kilometers long, then a huge gap in the valley. And then we have this 3 meters high, but only 600 meters long. So here you see a DEM of these 600-meter long ruptures, right? So it's not an overlay over this map. It's just a local DEM, 600 meters. Here, this is the fault scarp that happened in 1992, 3 meters high, 600 meters long. And this is an old riverbed, and the river was diverted by the fault scarp actually, but the scarp is still preserved, as you can see it. Now what would happen if we would feed these data in our Wells and Coppersmith earthquake scaling relationship equations, right? So there are these famous equations from their 1994 paper where you have the surface rupture length, and then you can get an idea on the moment magnitude. So just imagine if this earthquake would not have happened in 1992, but like 1,000 years ago, and we would go there as field geologists, find the fault scarps, and try to make sense of that. Well, what do we use? If we use 600 meters of fault length, we are somewhere here with a magnitude 5 earthquake. If we use 3 meters of offset, we end up with a magnitude 7 earthquake. If you only use the small ruptures in the west, we'll end up with like a magnitude 5.5 earthquake. Should we perhaps combine the western ruptures and then ignore the gap in the middle and add them to the eastern ruptures? This would then make them 25 kilometers long. Then we would be in the right ballpark, kind of, with our moment magnitude. But would we even be able to tell that this is the same earthquake if we came there 1,000 years later? Would we understand that these two ruptures belong to the same event? I don't think so. So if this was a paleo earthquake, how could we use these relationships? The ruptures are not continuous, they're highly variable, there's this huge gap. I think we'd get it totally wrong if we came there 1,000 years after the Susami earthquake. And another interesting thing is that in this valley, there are many more fault scarps. And this is again published in this wonderful paper of Eleanor Ainscough. So, for example, here in this area, there's this huge fault scarp. And it's about 2 meters high and it's really continuous and it offsets moraine and alluvial material. So we made a nice drone DM of that fault scarp. So here you can see it's a thrust fault and it's uphill facing, right? So the drainage direction is like that and the scarp is uphill facing. You can see that. Huh? Here's the drainage direction and there's the step. So this is the DM of the fault trace that we produced with our drone. And here, of course, you can see the fault scarp. Look how nice it is. Huh? It's really amazing. It's so beautiful. And you can see what we did here. We trenched it, of course. Sadly, there was no excavator around in this very remote valley, so we trenched it by hand. And well, after 2 days, we had our trench. And I quickly walk you through what we found in the trench. So this is the uphill facing scarp here, right? So the overall drainage direction is like this. And the trench is really easy. It's a very simple but very cool trench. I really like it. It's one of my favorite trenches I ever dug. So the first thing you see that there's the fault scarp, and there's the fault. So it's a thrust fault running like this. Why do we know that? Well, here we have fine-grained layered sediments, like really fine-grained, sandy, perhaps fine gravels, even silty a little bit. And here we have these coarse alluvial fan deposits, right? These things here. At the base of the trench, there are alluvial fan deposits, coarse boulders like this. And we find these on the other side of the fault down here in the trench. So it's clear that these things went up on the fault rupture, okay? So that's the first thing. And this is the slope direction. Now, another observation from the trench is that we have deformation here in these fine-grained sediments. So this picture shows you deformation. Look at this pale brownish layer here. It's deformed. It's a little bit folded. So I've marked it for you here. So, and then we see even more deformation. So this is from here, and you can see the dark layer. They are faulted, but also folded, right? So there's deformation in these fine sediments. And there's even, yeah, okay, so there's deformation in the fine sediments. And this tells us the story of the trench, actually, because we now know that there are at least 2 earthquakes preserved in the trench. Why 2 earthquakes? Well, the older earthquake, the first one, you needed to create the step in the landscape. Why? Because we have all this fine-grained material here and it needs to pond against the scarp, right? If there was no scarp, you couldn't deposit these fine-grained things. So you first need to create the sediment trap. It's the first thing. And then after that, what we found is that the fine-grained sediments that came in, they are deformed themselves. So you need a second earthquake to do that. You need the first one to dam it and to produce the sediment trap, and then you need a second earthquake to deform the sediments. And how did we date them? Well, we have radiocarbon and OSL dates. Down here, these things are about 5,000 to 8,000 years old. So here's a radiocarbon sample that's 5,000 years. And here we have here we have OSL samples that are 8,000 years. And here the uppermost sediments are about 3,000 years. So we have 2 earthquakes within the past, say, 5.6, in the past 8,000 years or so, that ruptured the surface and affected our sediments. Plus, we know about the 1992 earthquake. And the thing is, this fault, the one that we trenched, it did not rupture in 1992. And actually, there are many more fault scarps out there. So here, again, that's the 1992 rupture over here, and the other one would be somewhere here, you can't see it. That's the one that I just showed you. And all these lines, there are other fault scarps that we found in the valley. And we even trenched some of them. And the problem is they don't rupture in a big earthquake at the same time. So in 1992, we had a magnitude 7.2 earthquakes, but most of these faults did not rupture, only these ones. And we also know that the earthquakes that we found here in the trench did not rupture these faults or the others. So this is really complicated, right? So the next earthquake in this valley might rupture this fault, or perhaps this one, who knows? Or this fault, or this one again, or this one. And it's really impossible to forecast that. So it's a weird fault system there in the valley that really gives us a headache. So we know that there are lots of active faults, but why some of them rupture and what the rupture pattern makes so complicated, this we don't really understand. Okay, time to conclude the second part of my talk. So again, same as we learned in the first part, the hazard there comes from many different faults, and that's also true for the overall tectonics picture. There are many faults that are active. All of them can have strong earthquakes, but it's really hard to find them. And you really need to go to the field and combine a lot of methods to find them. Not all of these faults have ruptured in the Holocene because they have long recurrence intervals. The ones that I showed you had Holocene ruptures, but we know of other faults in the Tian Shan that we also trenched, and we saw that they have earthquake recurrence intervals um, um, on the scale of like tens of thousands of years. So you found a fault that had 2 earthquakes in the last 40,000 years. So this means if there's a fault that doesn't have a fault scarp, it does not mean it's not active. There can be a lot of active faults that just haven't ruptured in the past 10,000 years. And without paleoseismology, we'll never know. Also, historical earthquakes don't tell us the full story, obviously, so we really need this longer record. And we really need to combine a lot of different methods, and this is really the key in an area like that for understanding both the hazard, but also tectonics pictures. Now, all these DEMs that I talked about, they are available at opentopography.org, which is a wonderful website that hosts a lot of high resolution data. So you can just take a screenshot of the QR code and it will lead you to this wonderful website, or just type in the URL. And well, I'd like to thank you for your attention. And I'm very happy if there are any questions or comments, and open to a nice discussion. Thank you.
Right, thank you very much. Yeah, excellent.